about, well, I would say it's about a few examples. How come is it so noisy today? What happened? Is there anything going on? So it's normal. Did I remember this being so noisy? So, what is still missing before we can start talking about radar imaging is one or two examples about radar systems, and then the concept of detection, and then the concept of Doppler. So if I'd be fast enough, we will be able to see everything today. So, let's see. I think I can start with an exercise, which just give me the time to translate it, and I will upload this on the Dropbox folder. So this is about a radar for detecting aircraft. And so you have the classical radar that people image. So you have an antenna which is rotating, and as it rotates, it transmits and receives pulses. So you have a system of this kind, more or less. More or less clear. And so some data, you have an antenna of 3.0.5 meters. You are working at the frequency of 9 gigahertz. And the text asks you several things. So the first thing is that you have to be able to detect a target with a radar cross section of 10 square meters at a distance of 50 kilometers. Ensuring a signal-to-noise ratio of 14 dB. And so what you want to do is to determine what is the power that you have to transmit. So the transmitted power is 1 nano. And other data are that the noise figure of the system is 3 dB, and at 50 kilometers you can assume an attenuation due to the propagation in the troposphere equal to 3 dB. So let's say, how shall I call it? Alpha. So this is the noise figure. This is attenuation 2 ways due to the tropospheric propagation. And so you want to determine how much power you have to transmit, and then your minimum range, and I will comment on this later on, and the rotational speed. Let's say V rotation. Okay, so another data that you have is that your maximum, your non-ambiguous distance, or your first ambiguity, has to occur at 200 kilometers from the radar, and that you have a duty cycle of 20%.
What is error number?
Yes, I will.
Okay.
Not now, but in a few minutes, yes. Okay, so the first thing is to understand this minimum distance and this ambiguous distance, which is your question. Now, how do these systems work? Basically, you have an antenna which is rotating. As it rotates, it transmits and receives. And we will simplify the system a bit in our mind for the time being. And so we will assume that let's say that the antenna motion is frozen. You transmit, receive, and then you move. This is of course not the way it really works. The motion is continuous, but since the speed of light is so much larger than the rotational speed, then you can approximate the system this way and just assume that it's standing still, transmit, receive, changes position, and so this is called in the radar jargon the start-stop approximation. So basically you can neglect the geometrical changes in the system geometry in the time it takes for the wave to go to the target and get back. And then, so it means that you are transmitting a pulse. So let's say that this is a time diagram. You are transmitting a pulse here, and so this is your transmitted signal. Imagine that you have just one antenna, so you want to use the same antenna for transmit and for receiving the signal. So the first thing that you want to ensure is that you are not transmitting and receiving at the same time. Of course, you can discriminate the signal depending on the direction of the waves. So if the waves are propagating backward or onward, but you always have a leakage which can be several tenths of dB. So in general, you never transmit and receive at the same time. So the first thing is that you want to ensure that the signal the first echo doesn't happen while you are still transmitting. And so if this is the transmitted signal, this is the received signal, and you want the closest, let's say, you want that the closest target at which you want to be sensitive gives an echo which cannot fall before this time. Okay. Before, if the target is closer and then this echo happens, for example here, this is not big deal, but you can just you will just lose this signal, because in this time interval you are using your antenna to transmit So you're not sensitive. And so this is in time. Let's say that is t, how shall we call it? T0 or t observation. This is the length of your course. And so you want that the first delay happens at least at t ops seconds. And this of course sets the minimum distance at which you are sensitive. So your minimum distance will be half the speed of light times the length of your course. Okay. Now, if you think of a single course, then you can just wait forever until Nico gets back at you. But in truth, you are transmitting many courses. So you have the first course, then you change your angle a bit, and then the second course, and the third one, and so on. And so this means that the diagram of your transmitted signal is in truth something like this. So the first course, the second one, and so on. And this is called the pulse repetition interval. And its reciprocal is the pulse repetition frequency. So, imagine that you have a Nico here. The first question is this a Nico from a close target that is reflecting this pulse, or is this a Nico from a far off target which is reflecting this other pulse? You just don't know. And for this reason, this is called ambiguity. And your ambiguous distance or ambiguous range is just this time interval converted in meters. So your ambiguous range is half the speed of light times the PRI. So this means that let's say in this case, based on the text of the problem, we are working under the assumption that there is no chance that the target farther away from the radar more than 200 kilometers can be the return. And so in this case, it is considered a safe distance, 200 kilometers. So to ensure this safe distance, just set the PRI such that this equation is verified. the duty cycle is nothing else than your observation time divided by the PRI. So in this case, the duty cycle is 20%, which is a lot, by the way. Yeah, I mean, this is just an exercise, but I would say that a typical radar system of this kind works with a much shorter duty cycle, and we will see why in the second part of this lecture. And so, since the duty cycle is 20% and your ambiguous distance is 200 kilometers, then your minimum distance is just 200 by 0.2, and so it's 40 kilometers. Tell me.
Il raggio minimo da dove è stato calcolato?
No, this is, let's say, if you go, okay, this is time, right? What does a radar do? A radar translates time to space according to the speed of light. So if I multiply this by half this speed of light, then I get space, distances. So in this case, this is your minimum distance, and this is your ambiguous distance. Okay, the cycle is the ratio. So in this case, since the text is requiring you that the ambiguous range is 200 kilometers, and the text tells you that the duty cycle is 20%, then your minimum range is 40 kilometers. Just a second. Which means that if there is a target any closer than 40 kilometers, you will just lose it. It can be a tank, it can be a bomber, you just will not see it. Please.
Since the reflection inherits the main shape of the transmitted signal, why not to remove that ambiguity, we use the sequence of different shapes?
This you can do it. Yes, of course. This is a trick that you can use to remove ambiguity. Let's say this can work in some cases. Maybe in these cases it does work. But let's say in the context of a more general formulation, we just say that this is an ambiguity and you just don't know. But in this case, where we are assuming just a single target, so in this case where all our space is filled with a single radar and a single target, you're right.
You were Rmin in the graphic. Shouldn't be 2 times Rmin, which is corresponding to the T0, since it goes back and forth to the signal.
Take it again.
Since the signal has to go towards the target and then backwards, shouldn't be Rmin type T0 corresponding to 2 times Rmin, as you wrote before.
So T0 is 2 times Rmin divided by the speed of light.
Yeah, this is my point. So
okay.
why you in the graphic?
And this is written there. No, wait. those are seconds, those are meters. So of course the conversion factor is half the speed of light.
Okay, so we are considering out the speed of light
Yes.
in conversion. Okay.
Otherwise I couldn't even compare them because they are different units. Okay, so this is just to explain this jargon, more or less. So now we say, now I think that you know everything needed. You have to ensure a signal to noise ratio of 14 dB, we say. And you have to calculate how much power you need. So, which are the equations we need to compute this signal to noise ratio? The signal to noise ratio is this is something we saw last time we met. So it is the received power times the length of your pulse divided by L0. So divided by the spectral density of the noise. So in this case, N0 is the Boltzmann constant times the temperature. You can just assume here 290 Kelvin, unless otherwise specified, times the noise figure. And your received power, the radar equation will tell you your received power. This is equal to the transmitted power divided by the spherical divergence squared, because it's back and forth, times the gain and times the area of your antenna. Oh, sorry, and times the radar cross section of your target. I am neglecting here any. Neglecting here the antenna diagram. Okay, this is done for sake of simplicity. Then, of course, if you want to do a better solution, and then you should also consider here the diagram of your antenna. So we have the area of this antenna. The gain is nothing less than the 4 pi the area divided by the wavelength squared, and the wavelength is the ratio between the speed of light and the frequency you are working at. So when you put all these equations together, then you have all the ingredients that you need, and you can just solve this problem. So in particular here, if you put in some numbers, then you will find that your observation time is where is that? 266 microseconds, which is quite long again, because this duty cycle is very large. So, what else? Your N0 in dB is minus where is that? Minus 201. and the ratio between the transmitted and the received and the transmitted power, which is given by the Euler equation, is such that your transmitted power is where is that? Is equal to the received power in dB plus 159 dB. So you put all of this together, and since this in dB, since the signal to noise ratio in dB has to be 14, and if you want, you can translate this in dB, and you get minus 35. And so when you put all of this together, you get that the transmitted power in dB is equal to minus 201 plus 125 plus 35 plus 14. So the 35 comes from here, the 159 comes from here, and this is the noise spectral density, and this is the signal to noise ratio we want to ensure. What you get is that I didn't convert it in dB, so this should be about 8 dB. Right. Thank you. So the transmitted power in watts is about 6 watts. This is what you get. Okay. This is a very low figure. I would say that if you go in a real airport, then you will sense a much higher power on the radar. But in this case, you have a very low figure because the duty cycle was very large, so you can integrate your power for a lot of time, which means that you can win energy even if your power is low. Okay, so the other point was about the where is that? So the other one was right. So the other question was about the speed of rotation of this system, Is that okay?
So I'm experiencing some difficulties about the units.
This is dB.
dB,
This is what?
dB watt or dB
dB watt? Yes. dB watt, yes. Otherwise it's dBm. But in some cases, yes, in some cases you write like this, but for me dB is in watt. And of course, we are also converting a time in dB, which is weird, but you can just say that for example, if energy is power times time, then your energy in dB is the power in dB watt plus 10 log 10 of the time. So this is not dB watt, but it's clear. Okay, so the question about how fast this antenna has to go can be solved this way. So for each position, now imagine that I am looking at my antenna from above. And so you have a piece of metal this big, and this for us was 3 meters, which is rotating. Now for each position you are emitting power along a certain beam, which is more or less the wavelength divided by this length. And so in this way you know how many positions do you have to cover to fill in the space. And of course you need you don't want to leave any hole, so you need as many positions as, okay, so the number of positions is 2 pi divided by this angle, which in this case is about 565. And so if you want to set the rotational speed, then you have to consider that for each angle you want to give the time, you want to give the signal the time to go and get back. So the radar has to dwell in each angle a time equal to the PRI. Okay, so for each angle you need PRI seconds. And so it means that you need so the speed is you have no, wait, it's the other way around. So you have and this should be some 1.3 rotation per second. Okay? So it was a simple exercise. Now, this was an exercise with, let's say, so the text gave you all the information you need, and the text also made all the decisions for you. Huh? So this is just an academic exercise. What you need to be engineers is not just to be able to solve this one, but also to make your decisions. And so to do that, we should start talking about detection. So we saw here that you wanted to ensure a signal to noise ratio of 14 dB. Why? Why is that 14 and not 2 or 100? Huh? So what changes with the signal to noise ratio is that your signal, so the absolute value of your received signal, may change from this, so where you have your perfect signal without noise, and so this is a very high signal to noise ratio. And then you have some perturbation or a complete mess. How do you quantify this? Well, if you want to detect the target, what you do is to study the probability to detect this peak in your signal. Okay, so what I want to do now is to study the probability to actually see something in my signal. Now, how do we do that? Well, we stick to the most simple rule. So we just imagine that we set a threshold, and then we say that we detect the target if this peak exceeds the threshold, or we just miss it if the peak is lower. So in this case, for example, we would detect the target, we would also detect it here. If we have a lot of noise, you see, in this case we have many peaks that look like targets, but they are just noise. And so this situation is called false alarm. Basically means that you are freaking out and calling up your boss and say, we are under attack. No. This is just noise. And the other situation, of course, is if you want to avoid this situation, so if you don't want to look stupid with your boss, what you do, you raise this threshold a lot, so you are sure that you will not get any false alarm. And you set the threshold here. There is no false alarm here. But of course, you're also missing the target. So when you are for real under attack, you will just be there whistling and getting a coffee, and you will just not know. Right? So this is all, this situation is missed detection. So, what we want to do now is, well, we start saying that we just want to study this problem. You saw now that the problem, we're starting to cast this problem in mathematical terms by saying that we want to set this threshold. And we want to set this threshold. Of course, if you want a 0% probability to not to miss any target, then you should set this threshold to 0. In which case you have a lot of false alarms, and vice versa. So you want to set this threshold according to some criteria, but you want to quantify this. So you want to say, I want a probability of, I don't know, of false alarm of 10 to the minus 6, and the probability of misdetection of 10 to the minus 9. So you cast this requirement, and so you can set the threshold and see which signal to noise ratio you meet. Which means again that given a certain class of targets, so given a certain range of value for the radar cross-section of the target, then you know how much power you need. And this is an engineering work. So your task is just, I want to detect, I don't know, a car with good performance. You say, okay, a good performance for me is a certain probability. I fix this probability. I can see what is the radar cross-section of the car. I know my antenna, and then I know how much power I need. Okay, so this is the difference between real engineering and an academic exercise. So, how do we do that? Again, where was that here? So, we say that we want to use the math, and so we go back to the expression of the signal intercept. So we say that your signal, your received signal is something of this kind. You have, let's say, a certain amplitude times a pulse. Times a phase, which of course will not matter too much here because we look at the absolute value, times noise. This is after matched filtering. No, matched filtering. We just look at the absolute value, so the expression that we will be considering is this one. So imagine that you have your signal here. Times noise. You get a situation like this. So, first thing first, the probability of false alarm. False alarm means that you are, you think that you are seeing a peak while it is just noise. So, for example, here I can consider a time interval where there is no signal because this peak has gone to 0, and so you have just noise. So, if you want to study the probability of false alarm, then you have to study a random variable, which is the absolute value of noise. And so your probability of false alarm is nothing else than the probability that the absolute value of noise exceeds your threshold. As simple as that. Yes?
Okay, but when you say that that waveform is after the max filter, so we are assuming that the G is already the autocorrelation of the code.
You're right.
Okay.
That's right. It is good. Okay, so you remember that we say that your noise is a circular Gaussian noise, which means that any sample of WT is distributed as a complex normal variable, zero mean with some power sigma square. And this is the result of the real and the imaginary part of the noise, and we assume that both x and y are normal variable with some power sigma square, which is equal to sigma square of w divided by 2. So half the power is in the real part, half the power is in the imaginary part. Okay, and this is a J. So we have the statistics of the complex noise. We have the statistics of its real and imaginary part. Do you know the statistics of the absolute value of noise? No clue?
Must include the expectation of the square root of x squared plus epsilon squared.
Well, actually, if this is the real part, this is the imaginary part, then your complex noise can be a point here, right? Okay, we are assuming that, no, wait. So the absolute value of the complex noise is square root of x squared plus y squared, right? So the complex value is actually only the radius, the distance from the center, right? So the probability that the complex value falls into a certain interval is equal to the probability that this pair of random variables, so the x and y, fall into some circular curve like this. So let's say that this is R, this is dr, so this is a small portion of space, and the probability that this falls between R and R plus dr is equal to the probability that this pair of random variables bring you in this region. And this probability is easy. This is just the integral of the joint probability of x and y in this region. The joint probability of x and y, since they are Gaussian, So let's say the probability of x is Gaussian, so it has this form. The joint probability of x and y is just the products between the two, and so it is this expression. And you may notice that this is exactly the squared radius. So the probability that the absolute value of noise falls here is equal to the integral of this function here. So in this shaded area, and this is equal to 2 pi slash 2 pi sigma square times there. So this is the probability that if you want the probability, the density probability function, then you have to divide this by there, and so the let's say oops, times r, sorry. Here it is. And this is the famous Rayleigh distribution. I was very fast and I did not comment too much on this because this is signal theory. So who took the course with Professor Prati? No one? Everyone? Okay. Okay, so this was just to refresh your memory. If you have specific question on this, just ask me after the classes. Now, usually one also makes reference to. So in this case, sigma square is the variance of the real part. If you want to write this in terms of the variance of complex noise, then just remember that the variance of the complex noise is twice the variance of the real part, and so you can express this as a function of the variance of the complex noise. Here we have a factor 2, sorry, this way. And so this is the distribution of the noise power. It is more or less done this way. if you want to compute this at this point, all you need to do is to integrate this between your threshold and plus infinite. Which yields what's the idea here? So
2r squared divided by sigma squared. It was like that. Oh, I missed.
here we are.
What happened? Shouldn't there be a 2 in the exponent?
No, there was a 2 in the this is the argument of the exponential in the joint distribution of the complex and imaginary part of the noise. There is a 2 here, where this sigma square is the variance of the real part of the noise. If you want to write this as a function of the total variance, then and this is what you get. So you have now a mathematical expression for the probability of false alarm. So for example, if you know the noise power, then you want to set a certain threshold to ensure a certain probability of false alarm. All you need to do is to invert this equation, and what you get is that your threshold is the square root of minus variance of noise times the logarithm of your probability of false alarm. Beautiful, no? So you know so much more now. Huh? Okay. All you have to do now is to measure the variance of your noise. So just spot a time interval in your signal where you think that all you have is noise. Measure its variance. Set a probability, and here comes your threshold. It's beautiful. It's simple. Now, this is false alarm. What about the misdetection? Well, okay, here I have. Okay, for the remainder of this part, I will talk about. We talk in terms of the probability of correct decision, which is simply the 1 minus the probability of missed detection. And this is of course equal to the probability that your signal is actually taller than the threshold where you do have the peak. And so in this case, this is the probability that the absolute value of your signal plus the noise is larger than the threshold. So we need this. We need the probability of this random variable. Now this random variable, a complex Gaussian random variable plus a number. This is a bit more complicated because the absolute value of this variable gives a probability distribution which is called Rice. So let's call this A. So the probability of A is known as, the density distribution of A is known as Rice. It doesn't have the closed form expression, so I won't go with calculation. It is of course always positive because it is an absolute value. So it is done more or less this way. And let's say if the signal to noise ratio is very large, then you can approximate this as a Gaussian. And you can see it here. So imagine that we want to represent these two numbers in the complex plane. So this is the real part, this is the imaginary part. This is S. And the complex variable that comes out of this sum is S plus the noise. So you can see that the noise doesn't impact on the absolute value of S as long as the direction of noise is orthogonal to the direction of S. So it only impacts on S when it goes in this other way. So you can approximate this. You can approximate this by saying that this is a Gaussian variable, a real Gaussian variable, whose expected value is the absolute value of the signal in the absence of noise, and the variance is just given by the component of noise along a single direction. And so this is half the variance of the noise power. Half the variance of noise. Now, the signal to noise ratio, we define this as the peak of the signal squared divided by the variance of noise. And so the signal to noise ratio is, here is absolute value of S squared divided by sigma squared W. And so at this point you can calculate whatever you like. So you have the ingredients to do this calculation with your PC if you like. And it's very interesting, for example, to do this graph. Usually you put here the probability of false alarm, and here the probability of correct decision. So of course this will go to, let's say, 0 to 1 and 0 to 1. So for any fixed value of the signal to noise ratio, you can draw the probability of, let's say, what I want to do is I fix the signal to noise ratio. Okay? So this means that I can, for example, assume that the peak is 1, and so if I know the signal to noise ratio, then this means that I know the noise power. So this is just 1 divided by this signal to noise ratio. So I know this, I can set a certain V threshold as a function of the probability of false alarm that I want to set as requirement. Once I know this, I can also calculate the probability of correct decision. So for any fixed value of signal to noise ratio, I can calculate the probability of correct decision as a function of the probability of false alarm. What I get is something like this. So at around 0 dB, no wait, around 5 or 6 dB, I should get more or less something like this, or no, it's not this. So around 5 or 6 dB, I should get something like this. So approximately they are equal. When I go to a lower signal to noise ratio, say 0 dB, then I find something like this. So what does it mean? That if your signal to noise ratio is very low, then to have an acceptable probability of correct decision, let's say on the order of 0.8, 0.9, then you have to accept a very large probability of false alarm. There is no way out of it. If your signal to noise is large, let's say it's 10 dB, then it is the other way around. Your signal to noise is large, and so there is no need to stay here to ensure a good probability of correct decision. You can just stay here and have a very low probability of false alarm. And of course, the higher the signal to noise ratio, the more this curve will behave like a, how do you say, like a wedge, huh? Like this. And of course, the other way around. And so for example, in this way you can totally design your system based on this concept. Let's say now the last thing to discuss is what you define as an acceptable probability of false alarm or an acceptable probability of correct decision. And this, of course, let's say this is where engineering cannot give you an answer, and you have to resort to your common sense, or you say to your gut, to your feeling. I had excellent professor of remote sensing years ago, and he explained us this choice in terms of hunting. So, are you hunting for ducks or are you hunting for bears? If you are, you know the story, no? You're smiling. You know the story already.
But I know from you, so it's
For me.
yeah, Bachelor of Aerospace Engineering.
So you know it all now. Okay. Don't tell it. Okay.
Yeah.
So the story is, if you're hunting for bears, your first concern is that the bear is not hunting for you. So you want to be absolutely sure that you are detecting the bear when he's about to eat you. So if you're out for hunting bears, then you want a probability of correct decision which is very, very high. It doesn't matter if you have many false alarms. So I prefer to be scared and think that instead of the wind in a bush, there is a real bear. So I prefer to get scared many times, but I want to be sure that when there is a real bear, I do detect it. Okay? If you are hunting for ducks, then you have the opposite problem. So your first concern is not to waste bullets. And so you don't want to shoot every time for a false alarm. So you don't want to shoot for every little noise in the forest or in the wood or wherever ducks live. So in this case, you want to reason the other way around. And so you have a very low probability of false alarm, and you can accept that you will miss a few ducks. Okay, so it depends on your application in the end. For example, it may change a lot if you want to detect a car, for example, for measuring its speed, or if you want to detect a missile or something like that. Okay, so I think this is it for now. I was very ambitious because I thought I would also start the part on Doppler radars, but I have just a few minutes and it doesn't make sense to do it now. So I leave the floor to you for questions in case, or we just meet on Monday and we do Doppler radars.